Assalamu alaikum.
Assalamu alaikum.
We'll wait another 2 minutes for the rest of our colleagues. Any question regarding yesterday's lecture? Any further question?
No, sir, it was all clear.
मेरी तो इनसे बात ही नहीं हो रही, मैं तो अपने में फंसी हुई हूँ।
So let's start our lecture for today. Yesterday we already discussed about ultrafiltration. Let's summarize what we talked about yesterday. It is, as I said, ultrafiltration just used for the separation of particles, large molecular weight molecules over 5 nanometer. This in general. This in general, and we said that we referred to those two figures. One, as I said, with the minimum limit, and the upper limit is 1000 micron, and the other one with lower limit and maximum limit range between 150 to 300 micron. So these two figures will come back to them later. As I said, I will clear them why I mentioned those two figures as shown. So we already discussed, as I said, the classification of ultrafiltration membranes. We said that 3 types of material can be used for it. The first is polymeric membrane, traditional polymeric membrane, consisting of cellulose acetate, consisting of cellulose acetate, polyvinylidene fluoride, polysulfone, even Teflon. As I said, many other material can be used. Hydrocarbons can be used as a material for polymeric ultrafiltration membranes. Then we said that the other category is ceramic membranes. Ceramic membranes found in 4 types. The first is zircon oxide, titanium oxide, silicon carbide, aluminum oxide, alpha aluminum oxide, as I said. The third type or third category, the third category is hybrid which can be either polymeric or ceramic membranes with, as I said, some modification regarding the coating to give special characteristics for the surface, regarding hydrophilicity or some additional, as I said, characteristics regarding the pore size, the flux, and to match or suits other application, special application like pharmaceutical industries, oil removal, many other applications. We already said that each type of those can be classified further for in more detail. For example, the polymeric membrane, we can classify it to flat sheet, hollow fiber membrane, and hollow fiber membrane. The hollow fiber membrane, we classified it as for today, submerged and pressurized. This the new information which we'll give today. And then we said that the two main types of or techniques of ultrafiltration or filtration, which is the dead end filtration and cross flow filtration. The ceramic membranes also can be categorized into two categories. The first one, which is tubular membrane. The second is flat sheet membrane. Both of them can be, as I said, dead end filtration or cross flow filtration technique can apply for it. What we want to mention today about the application for these types of membrane. It can be, as I said, pressurized or submerged, pressurized or submerged. We'll discuss it in detail in our lecture, the pressurized type and submerged type. Submerged type should be inside tank, and it work either by, as I say, suction from inside of the module itself or the membrane itself, so the retentate or the residue should accumulate on the outer surface of the membrane. The other type, which is pressurized, we say that it's working with, and the submerged, by the way, working only with dead end filtration, technique. The pressurized can work with dead end filtration or cross flow filtration, either dead end filtration or cross flow filtration. The hollow fiber membrane, for the polymeric membrane, we categorize it to flat sheet, which is, as I said, should be always submerged inside tank, and working with sucking technique. The hollow fiber can be submerged or can be pressurized. The pressurized type inside pressure vessel can be mounted on vertical position or in horizontal position. It can be also cross flow or dead end filtration systems. So this is simply, as I said, the groups or how to group or classify ultrafiltration membranes. Any question regarding these points which I mentioned? This is, as I said, the dead end filtration. This means all the amount of fluid, or let's say for water as example, pass through the membrane surface. This means there is filtrate side and there is feed side. There's filtrate side or feed side. This can work either by a pressurized system. This means there is pressure applied, the fluid or the feed water applied with pressure from feed side, or can be, as I say, sucking, which is the feed side will be pressureless, and the permeate or filtrate side should have negative suction. Sucking pump from this side. The cross-flow filtration, we said that there is a feed stream and there is a retentate. The feed stream, this means the water bus or the fluid bus parallel to the membrane surface, and during its passage, it's started to infiltrate or filtrate through the membrane surface as shown in the figure. So we have in such a case, as I said, feed inlet pressure, and we have retentate pressure. Here we have the 100% of the amount of fluids or water exist in the feed side. There is a certain amount to be filtrated as a permeate, and the residue, which is the retentate, has smaller amount. We can consider this amount of permeate divided by the feed stream amount as a percentile. This gives what we call recovery percent. So recovery percent term apply only for cross flow filtration, but in case of dead end filtration, it's always 100%. Okay. Regarding the dead end filtration, we also pointed out that in case of suction from filtrate side across the membrane surface, the cake layer accumulated will be just friable, easy to remove, no much, as I said, infiltration inside the membrane texture or membrane material. But in case of the pressurized system, the cake layer will be too much compact because it's pressed against the membrane surface. Some tiny particles, which is equal to the pore size of the membrane, will be infiltrated inside the membrane surface and the material as shown in the figure. So this is the main, as I said, difference between the two categories. If we check this figure, it shows us the dead end filtration against the cross flow filtration. We can see here, this is the time, and we have here two axes. The first one, which gives the cake thickness, and from the other hand, we can find the flow rate. So we have time in between of cake thickness and flow rate. So we can notice that easily that the flow rate started to decline gradually with time, while the cake thickness started to increase due to the build-up of the cake layer on the membrane surface. This is for dead end filtration. But for cross-flow filtration, similar thing happen also, but we can see it in different way. We have the flow rate, okay, decline also, but of course not much as in the dead end filtration, and the thickness also of the cake layer is a little bit thinner than in case of dead end filtration. So this is the main, as I said, differences between the two techniques or the two types. Let's go to this. We already, as I say, said that for the hollow fiber polymeric membrane, it exists as shown in the figure, either to be submerged. This is the hollow fiber, as I say, polymeric membrane, and we can see this flat sheet. This is a flat sheet. This is a hollow fiber, which we can see here. This is the hollow fiber polymeric membrane. So we have the hollow fiber polymeric membrane and the flat sheet membrane. The hollow fiber type can be, as I say, either to be submerged like this, or can be inside, can be mounted or fixed inside the pressure vessel. How to be just fixed inside the pressure vessel? We have the tubes or the hollow fiber tubes. We can see a reason around it mounted from the cap side from both ends, and we have the hollow fiber in between. So it can apply. We can see this is the final figure. or the final shape of the membrane module here in this figure. We can see there is a feed side, and we have the concentrate or retentate side, feed side, retentate side, the flow coming in this direction from feed to retentate side. And in the same time, the permeate or the filtrate goes from upper and lower inlets. So it go from upper or lower inlets. So in such a case, what can we call this type of filtration? Cross flow or dead end filtration? Somebody answer? Of course, this is we call cross flow filtration. This cross flow filtration, as we see here, the water or the fluid pass from the bottom side to the upper side. It increase in, as I say, in the content of the particulate or TSS or whatever inside of it as a contaminant. And in the same time, as I said, we have permeate. What happened if we closed this retentate outlet? If we closed the retentate outlet, it will be used as a dead end filtration in such a case. So this, as I said, system can work as dead end filtration or can be used as a cross flow filtration. So this can be used, as I said, as dead end filtration or cross flow filtration, as we see. In the same time, we have another thing, which is here we stated that this is the feed side and this is the retentate side. Can we exchange it between this permeate to be here feed side and here retentate side, and we can use both ends for filtrate or permeate? Yes, of course. We can see in this figure that the fluid or the water or the feed water coming from outside of the hollow fiber and start to infiltrate inside the tubes, and the particulate or cells or bacteria, viruses, any colloidal material will be retained on the fibers from outside. So in such a case, it means that we use, as I say, both side, this side connector as one for the feed, one for the retentate. And from the other hand, both of the two ends, top and lower one, for permeation or for filtrate. So this is, as I said, this in this case, we have from outside to inside flow, from outside to inside flow across the hollow fiber. Let's see the lower part, the lower one here. I can make it bigger a little. We can see that the feed in such a case pass through the fiber itself. So it passes inside the fiber from inside, and the filtrate started to pass across the membrane surface from inside to outside. So this is the opposite of the first case. We have from the first case, it's from the filtration process take place from outside to inside. We have the filtrate inside the fiber. But in such a case, in the second case, we have, as I say, the flow from inside the tubes or the fibers itself, and the filtrate pass across the wall of the membrane from inside to outside. So I hope this clear this point regarding to the pressurized system. This is the pressurized system. It works under pressure, as I say, external pressure applied either from feed side, as I say, from outsider, in case of out to inflow, or inside the fibers itself in case of from inside to outside flow, as shown in the figure. So this is simply, as I said, the case. The fibers itself, the fiber diameter for the flow, of course, we can see the surface area is a very important thing because we have a flux controlled by the surface area, which in such a case considered as the outer diameter, which is the surface area from outside to inside flow, or the inner diameter in case of inside to outside flow. So this is the controlling, as I said, factor in the, as I said, the membrane surface area, the number of the fibers, and in the same time, the diameter of the tubes or the fibers itself. We can see for some types, we have this very tiny tubes range in between 0.8 to 1.2 millimeter. But is there any fibers with larger diameter? Yes, of course. We can have fibers with larger diameter, as I will show for you. 5 millimeter and 8 millimeter. 5 millimeter and 8 millimeter. This, of course, can be used for wastewater treatment or, as I said, very turbid or water with contaminant. So the main important thing that the hollow fiber membrane in such a case much suits the application which is used for it. It can be, as I say, used for filtration, for industrial water treatment, to remove some just chemicals or compound high molecular weight. So we have a simple issue not affecting the diameter of the hollow fiber itself, or can be, as I say, to treat turbid water, surface water like river water, or with contaminants, or even wastewater treatment like in the MBR, as we will see in the applications. Okay, so we have, as I say, different diameters of fibers based on the application for which it is used. This is, as I say, for the hollow fiber. We see it, as I say, can be used for cross flow. In the same time, can be used for dead end filtration. This is the hollow fiber inside the housing. We can see different shapes, different techniques according to the application can be used for. Some of it can be just for dead end filtration, and the other can be for cross flow, as we will see in some videos with us. So here also we can see the hollow fiber membranes. This is, of course, the feed water outside. This means cross-flow filtration. We can see the permeation around the fiber itself. It's closed or sealed from both sides just to allow, as I say, the feed water from one side, the retentate from other side, not to be, the filtrate not to be contaminated with the feed water pollutants or contaminants. So as I say, here also we can notice that it is from outside to inside, outside to inside. As I say, it can be used for cross flow, as in this figure, or dead end filtration. We can see in both sides of the figure. Here, this is from inside to outside filtration, or can be used from outside to inside filtration. So this in general for the pressurized hollow fiber membrane. So we have, as they say, the pressurized hollow fiber membrane. We already explained that it's a bundle of fibers just with resin from both sides. It's cut fair face or clear section on it, so we can see the fibers sides exposed already, and we can use this, as they said, inside pressure vessel. It can have like a sealant from